You might think the battle for AI dominance is happening in Silicon Valley. We spend all our time obsessing over the latest chips, watching stock prices for NVIDIA, and waiting for the next version of ChatGPT. But while everyone is looking at the processors, almost nobody is paying attention to the power outlet. There is a massive invisible wall approaching the AI industry, and it has nothing to do with coding or algorithms. It is about pure, raw electricity. The energy demands of artificial intelligence are skyrocketing at a pace that our aging power grids simply cannot handle. We are building digital brains that eat as much power as entire nations, and we are running out of places to plug them in. But a few visionaries have realized something profound. They realized that trying to fix this problem on Earth is like trying to make ice cubes in the middle of a desert. Why fight the heat and the scarcity down here when there is an infinite reservoir of energy and a limitless freezing void just a few hundred miles up? The next great leap in computing isn't happening in a server room, it is happening in orbit. And the race to build the first data center in the stars has already begun.
Let's look at the physics of the problem we face down here. Training a single cutting-edge AI model consumes an astronomical amount of electricity. We are talking about gigawatt-hours of power, enough to drain the resources of a small city. But getting the power is only half the battle. The real enemy of high-performance computing is heat. When you run thousands of GPUs at maximum capacity, they generate temperatures hot enough to fry eggs. To keep them from melting down, we have to build massive cooling infrastructure. We pump millions of gallons of water and run giant air conditioning units 24/7. It is incredibly inefficient. In a traditional data center on Earth, nearly 40% of the total energy consumed is used just to keep the machines cool. That is almost half the power wasted on fans and pumps. Imagine running a marathon, but spending half your energy just trying to fan yourself so you don't pass out. That is the current state of the AI industry. It is a thermodynamic nightmare. But now, imagine a place where you don't need air conditioning. Imagine an environment where the ambient temperature hovers near absolute zero. That place exists, and it is right above us. In the vacuum of space, you have access to a cooling system that no engineering team on Earth could ever build. It is the ultimate heat sink. And for the tech giants running out of options, it looks like the only way forward.
This isn't just science fiction or a distant dream. The biggest players in the game are already making their moves. Google has quietly unveiled something called Project Suncatcher. While most people missed the announcement, this initiative represents a fundamental shift in strategy. They're looking at deploying tensor processing units, or TPUs, directly into low Earth orbit. The logic behind Project Suncatcher is ruthlessly simple. On Earth, solar panels are limited by night cycles, clouds, and atmospheric interference. But in space, the sun never really sets. A solar array in orbit can generate power roughly 8 times more effectively than one on the ground. It is a source of clean, constant, and completely free energy. Google's plan involves creating a constellation of satellites that act as orbital data centers. Instead of pulling dirty energy from a coal plant, these satellites would drink directly from the sun. They would process data using the latest AI chips like the Trillium series and beam the results back down to Earth via laser links. It sounds insane until you look at the numbers. If you can eliminate the electricity bill and delete the cooling bill entirely, the economics of AI change overnight. You are no longer bound by the constraints of the power grid. You are only bound by how many satellites you can launch. And as we're about to see, launching satellites is becoming cheaper than anyone expected. For decades, the idea of space-based computing was impossible because of one stubborn number. the cost per kilogram to orbit. In the old days of the space shuttle, sending a single server rack to space would have cost tens of millions of dollars. It was financial suicide. Even with the Falcon 9, costs were hovering around $2,000 a kilogram. That is affordable for a communication satellite, but still too expensive for heavy computing hardware. But that math is being rewritten in real time. With the introduction of massive reusable rockets like SpaceX's Starship, we are approaching a singularity in launch economics. Industry experts project that launch costs could drop to as low as $20 per kilogram. Let that sink in for a moment. At that price point, sending a supercomputer to orbit becomes cheaper than building a new facility in California. You avoid the land costs, the property taxes, and the regulatory nightmares of zoning laws. Suddenly, the sky is open for business. This drastic reduction in launch costs is the catalyst that turns Project Suncatcher from a cool experiment into a viable industry. It allows companies to launch heavy, shielded hardware without bankrupting themselves. We are moving from a scarcity mindset to an era of abundance in orbital infrastructure. And once the cost barrier falls, the floodgates will open. Let's dig deeper into why space is the perfect home for AI. A groundbreaking study published in Nature Electronics by researchers from NTU Singapore and Zhejiang University laid out the blueprint for this new era. They analyzed the thermal dynamics of what they call the orbital edge. The study confirmed what physicists have known for years. Space offers a natural radiative cooling effect that is impossible to replicate on Earth. In the vacuum of space, heat doesn't need to be blown away by a fan. It can be radiated directly into the deep cold of the universe. The background temperature of space is roughly 2.7 Kelvin, that is minus 270 degrees Celsius. It is effectively an infinite freezer. By orienting the satellites correctly, shielding them from the sun on one side and exposing radiators to deep space on the other, you can run high-performance chips at maximum clock speeds without them ever overheating. This passive cooling means no moving parts, no fans to break, no water pumps to leak, and no vibrations to disturb sensitive equipment. The researchers found that this approach could reduce the energy footprint of AI training by orders of magnitude. It turns the hostile environment of space into the ultimate competitive advantage. We're talking about a system where the hardware runs faster, cooler, and longer than anything on the ground. We are already seeing the first steps toward this reality. Recent demonstrations have shown that consumer-grade hardware can survive and function in the orbital environment. There have been reports and tests, sometimes referred to in tech circles as star-clawed missions, where lightweight AI models are tested in orbit. Imagine running a model like Google's Gemma or a distilled version of Anthropic's Claude on a satellite whipping around the Earth at 17,000 miles per hour. These aren't just theoretical simulations anymore. Real hardware is processing real data in zero gravity. The goal of these early missions is to prove resilience. Can the memory chips handle the radiation? Can the power systems handle the spikes in computation? The results so far have been promising. By using distilled or smaller versions of these massive models, engineers are proving that you don't need a massive mainframe to do useful work in space. You can have a distributed network of smaller nodes, a swarm of intelligence wrapping around the planet. This allows for what is called edge computing in space. Instead of sending raw satellite images down to Earth to be processed by a server in Virginia, the satellite analyzes the answer instantly in orbit. It only sends down the answer. This drastically reduces the bandwidth needed and speeds up reaction times for everything from disaster relief to military surveillance. However, we need to be realistic about the challenges. Moving our digital brain to the stars is not as simple as launching a server and walking away. There are brutal technical hurdles that still need solving. The first and most dangerous is radiation. On Earth, our atmosphere acts as a thick protective blanket, shielding our electronics from cosmic rays. In space, that shield is gone. High-energy particles can smash into silicon chips, flipping bits and causing calculation errors. For an AI model, a flipped bit could mean the difference between a correct answer and total hallucination. Companies have to develop radiation-hardened chips or clever software that can self-correct these errors. Then there is the issue of latency. Even though light travels fast, sending data to orbit and back takes time. For real-time trading or gaming, that split-second delay might be unacceptable. And perhaps the biggest problem is maintenance. If a server rack breaks down in a data center on Earth, a technician walks over and replaces the part. If a satellite server fails in orbit, it is gone forever. You cannot send a repair truck to the ionosphere. This means the hardware has to be incredibly robust or cheap enough that you can simply treat it as disposable. And we cannot ignore the issue of space debris. Low Earth orbit is already becoming crowded. Adding thousands of data centers increases the risk of collisions, which could create a cascade of debris that traps us on Earth forever.
Despite these risks, the momentum is building. We are witnessing the birth of a new orbital economy. Just as the internet created a digital economy, space data centers will create a celestial one. Think about the implications for energy independence. Countries that are energy poor but technology rich could bypass their local limitations entirely. They don't need to import oil or build nuclear plants to power their AI ambitions. They just need to launch satellites. This democratizes access to high-end compute power. It also raises fascinating questions about data sovereignty. If your data is processed in international waters, or rather international vacuum, whose laws apply? We might see the rise of data havens in the sky, outside the jurisdiction of any single government. It is a wild, unregulated frontier. And the companies that stake their claim first will become the landlords of the future. They won't just be selling software, they will be selling the very infrastructure of intelligence. We are moving from cloud computing to what some are calling sky computing. The cloud is no longer just a metaphor, it is becoming a physical reality orbiting above us.
So, what does the next decade look like? We will likely see a hybrid model emerge. Your Netflix stream and your emails will probably stay on the ground, but the heavy lifting, the training of massive superintelligence models will migrate upwards. It makes too much sense to ignore. Why burn coal to train an AI when you can use the raw power of the sun? Why fight thermodynamics on Earth when the universe offers you a free cooling system? The transition has already started. From Google's Suncatcher to the secret tests aboard starships, the pieces are moving into place. We used to look at space as a place to explore. Now we're looking at it as a place to work. The next time you ask an AI a complex question, the answer might not come from a server farm in the desert. It might beam down to you from the silence of space. The battlefield for AI has shifted. We have run out of room on Earth. The only way left to go is up.